That's what do TikTok.
For body checks in the
Shit. Okay, cool. So, time for today. Bit of shrinkage, whatever that is, SCMs, intro to reinforced concrete. So talking about some properties of reinforced concrete and what's important in this course. Steel properties. There's also some durability requirements from like AS3600, fire requirements, all that kind of stuff, which I will cover. And then I'm gonna touch a bit on flexure, which is week 5, I believe. I actually didn't finish my notes, as you can see, but I'm gonna freeball it, right? Cool. Let's get started. Shrinkage. So, what is shrinkage and what causes it? So there's two main reasons for shrinkage. We've got moisture loss, and we've also got chemical shrinkage. So moisture loss is pretty much just evaporation of water, which makes sense, right? And chemical shrinkage is just due to the hydration reaction. Let me see if it's actually recording. Yes, it is. So you guys learned about hydration, and as that hydration reaction actually occurs, it causes change in volume, right? So the change in volume itself is what causes shrinkage, right? If you can imagine this water bottle, right? It's got some hardened concrete or like some like plastic concrete in it, which means that it's like wet still. Right? As it hardens, right? Okay, I don't know if you guys remember. Have you guys done materials? You guys remember the shrinkage part, right? No, I barely do as well. I can't lie.
No, the shrinkage was in construction.
Was it? Maybe it wasn't shrinkage. It might have been something else. But it was the metal as it melts and then dries, whatever.
Probably.
Right.
Yeah.
Like it dries from the inside and then it starts to shrink. Oh no, it dries from the outside, right? And then because of that, it pulls the material in, so the volume reduces, whatever. But that causes tensile stresses within the material.
Interesting.
Better way to explain it? A horrible way to explain it. I'll explain it again. Pretty much, as you walk.
Wasn't there like volume shrinkage, but then there was also like almost like dimensional shrinkage, and then there was also like ones where there will be pores, like there'll be like little holes inside.
We'll talk about it in this, but how do I explain it? Okay, the reduction in volume. Do you want to explain it? So pretty much the reduction in volume causes tensile stresses. Those tensile stresses cause the concrete to actually crack. Right? So we wanna don't look at me like that, Randy. We wanna avoid shrinkage because it like causes cracking, right? So delving more into moisture loss, there's two. We've got fresh concrete and hardened concrete. Fresh concrete being like what you just pour, right? Hardened concrete, it's in the name, hardened concrete, right? In fresh concrete, what are you doing?
This is my shit, man.
Okay, sorry. Fresh concrete, there's something called plastic shrinkage, and then hardened concrete is drying shrinkage. I'm not explaining what each of them are. Apparently not, I'm not. Anyways, so after the concrete has set, pretty much the pores that you're talking about, the water, all those kind of stuff, as it dries or the water evaporates, it causes shrinkage. Right? There's also plastic shrinkage. You don't need to really know each of these in too much detail. That's why I've kind of covered it, very generally, broadly. But chemical shrinkage is 3 things. There's initial setting, so when the hydration reaction starts during the initial setting. Autogenous shrinkage, which is something called self-desiccation, internal drying. Pretty much the pores, all that kind of stuff. The water, I'm not sure if you guys remember. This stuff? Yeah. So the water actually drying from here to here, or like from here to here, that kind of stuff. That's what we call self-desiccation. And there's also voids, right, which causes reduction in volume. So there's like this diagram here which kind of explains what chemical shrinkage is. There's 3 parts to it: autogenous shrinkage, voids, and some other bullshit. You don't know. I'll be honest, shrinkage itself, I'm not too tapped in with. So I'm just covering it pretty good. Like, the main thing to note, shrinkage causes tensile stresses, the outside fibers, which causes cracking. Randall, you got that? Causes cracking?
Yeah.
Dumbass. Okay, anyways. It's not that important. I'm gonna go to mineral admixtures now. SCMs. So what do they mean? Supplementary cementitious materials. They contribute to the properties of hardened concrete, and it's also better for the environment as your carbon dioxide emissions are very low compared to like regular concrete. So if you don't add SCMs, your carbon dioxide thing will be a bit higher. There's a couple different reactions. We've got a hydraulic reaction there's actually two main reactions you have to know about. So this is where the chemistry part kind of comes in. There's two that you have to know about: hydraulic reaction and pozzolanic reaction. So a hydraulic reaction is when your admixture reacts with water to form compounds that will have cementitious properties or cementing properties. So there are two main examples that's covered in the course. You've got OPC, which is ordinary Portland cement, plus water, which causes CHS plus CH. CH will cover later in the pozzolanic reaction. So this is a byproduct, a pozzolanic byproduct, which I'll explain as well in a bit. Then another example is slag plus water, which causes CHS plus other hydrates. So CHS, if you guys don't already know, is the main contributing product responsible for strength. Right? Pozzolanic reaction, silication.
What's slag?
I don't know.
It's like just another kind of
No,
cement.
slag is like a. I've got it here. Slag. Here it is. Slag is a byproduct of iron manufacturing. It's like a SCM. It's one of the cementing materials, cementitious materials, right? PM being a pozzolanic material which reacts with the byproduct that I was talking about earlier, and it causes CHS. It's a product, but what you guys need to know really is like the SCM classifications. We've got natural material and byproduct materials. I don't really want to cover this, but I'll be honest. This is just a whole bunch of theory. What really matters is how to use this table here, or this diagram. So you'll see in one of the final exams, they give you like, I'll show you guys an example. Yeah, we're running a class. Let's see, something like this. This is what I was talking about, right? Jen, what's so funny? Thank you, Randy. You see something like this, right? So it kind of, you've got you've got AlO2O3, whatever that is, carbon oxide, whatever that is, monoxide, and you've got this, which is also depicted on this diagram. One of the questions that you will probably be asked is, what are each of these materials? Yeah. So you can either take this into the exam with you. I think that's probably the best method to do, or like you can kind of memorize it and like kind of figure it out bit by bit. Yeah, so they actually give you the list of materials, and so this thing down here, this is just slag. So this is like the proper name for it, or you can just call it slag. Okay, I fucking hate this shit, bro. Okay, so this is like the Henry summary of SCMs. So you've got the material, slag, fly ash, silica fumes, and natural pozzolans. The origin, so pretty much where they come from. What kind of reaction it is, latent, pozzolanic, or hydraulic, whatever. The composition, and then the changes in concrete. So what kind of changes it makes to harden concrete, right? Why, like, if we add this, what happens to the concrete, right? So for example, if you add slag, you get better workability. Your early strength reduces, however, your density and bond is stronger.
Wait, does this hit
They might ask one question on it, so I don't remember. Let me take a look.
Depends if you mix different materials.
Sorry?
Why would it be much different? SCMs here?
You fucking explode.
It's just a method.
That'll go fine. Anyways, yeah, there's not really much to SCM. It's a pretty small topic. Okay, I'm gonna move on because I don't like that theory part. Now we're moving into like the design aspect, sort of, right? So it's still a bit of theory, but I'll explain. So properties of reinforced concrete. So there are two different materials in reinforced concrete. We've got the steel bars and we've got concrete. So I'm going to cover them separately. So concrete properties first. Something you guys should have covered that is quasi-brittle. That's a random ring a bell.
No, I haven't been done actually.
Jan ring a bell. Ray. Smash. What's quasi-brittle? What's quasi-brittle? I'm not explaining. It's like the failure mode.
Is it the rebar because it's reinforcement bar?
Oh, is it weaker, concrete weaker in tension? Stronger in tension?
Nope.
It might be reduced.
Wow. Well, you did it.
It might be. That's great.
So good for my company. Yeah. Why are you doing this? You did.
Okay, so these are the. Oh. So I think this is like stress versus strain. But this thing in the middle is the reinforced concrete graph. This one is just for concrete. This one is the steel. That looks hella long. This is sub-sub. What they say is a sub-sub. Yeah, so yeah, here it is. This is what I was trying to go. Probably should have added this in the notes. So this is the. Hey, what do these mean? I don't even know how I'm trying to explain this, but I don't even know. One second. Let me open up the lecture slides. Holy fuck! I have a lot of assignments. No, I don't. I got none. Oh, here it is. Oh, here it is. Here it is. Oh my god, it's right here. Okay, cool. So the failure mode, simple way to put it is like it's brittle, which means it cracks. It's not ductile. It's not like. But when you introduce the Rio in it, the rebar. Oh, by the way, Rio is reinforcement. The steel reinforcement. Rebar is also. There's just different names for the same thing, right?
Rio.
Okay. Rio, yeah. Rio.
R-I-O, like the bird movie.
R-E-O. 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 Rio.
Oh, okay.
Alright. No, I don't like this guy.
What if you not teaching us that line? What if that's in the test?
We won't be in the test.
What will you give us if it's on the
Is there
test?
compensation?
I'll show you guys a Molly
We all
two.
get to be tried?
No, don't be mad. I'll give you guys a Molly 2.
Oh.
Okay, anyways. Quasi-brittle is literally just one of the failure mode. It's like the fucking simplified like failure mode for concrete. It just means it's not quite brittle. It's like somewhere in the middle. It's somewhere in the middle. But the main thing to note is that it's much weaker in bending and tension compared to compression. So bending and tension means, so this is bending, right? Like that. So listen. And then tension being like it pulls apart. Really good. And then compression is like just pressing it together. Can I use a bottle for demonstration? Thank you. Yes. In fact, it's like 10 times weaker in tension and bending compared to compression. Fun fact. And because it is weaker, right, in tension and bending, that's why we put the Rio in it, to kind of strengthen the concrete itself. So when they act as a composite together, Rio and the steel and the concrete, they act together to kind of counteract the cons in concrete. So you can still act in compression, right? It acts pretty strong in compression, but in tension and bending, it's a lot more stronger now, right? Hey, so there are measured properties, empirical relationships, and also statistical properties that I'm going to cover. So measured properties meaning they do tests to figure out what these values are, right? So the most important one, so I've already talked about these three last week. Not last week, the week before. The uniaxial tensile strength, measured flexural and measured splitting. Jen, do you remember? Do you remember that thing that I drew out? That this is the cylinder, the thing pulling on each side.
Oh yeah.
That thing? Yeah, so the 3 different tests that they do. These ones?
Yeah.
Yeah. Oh, what the hell happened here? But yeah, then there's like these point loading tests as well, flexural tests. These aren't important at all. Right? What's most important is this: your characteristic compressive strength at 28 days. They use that pretty much everywhere when you're designing, like a beam, a slab, whatever. Because it's a property that contributes directly to strength of your concrete. Right? Empirical
Test
relation.
for that.
Huh?
How do they test for that?
How do they test for it? They got a machine for it, I think. Empirical relationships, you've got FCT, which means something. Uniaxial tensile strength, and like the direct relationship to these two. So as I was saying last week, that the uniaxial tensile strength is a lot more accurate, right? And it gives us like a higher strength compared to these two. These two aren't as accurate, and it gives you like a lower strength. But those are the 2 cons of it, right? The con of this one mainly, the downside of it is that it's really hard to perform and it's dangerous, right? However, it gives us a more accurate result. These two aren't as accurate, but it's like the repeatability is easier and it's safer, right? So they do these tests and they just kind of scale it down or scale it up. Oh, sorry, these ones give us higher results. This one gives us a more accurate but lower results. This one overshoots it, overestimates it. This one's pretty important. This one you might use in shear. These are just formulas at this point. And everything's given to you on the formula sheet. I'm just trying to explain to you. I'm not even going to explain anything. This one I'm going to explain though. Who knows what E stands for?
Elastic modulus.
Correct. Elastic modulus. Right? For some reason I forgot to finish off this formula. Okay, so elastic modulus, you guys have heard about it a lot. Usually in the AS 3600, they've given us this table, right? Meaning that depending on your characteristic strength, you get a certain elastic modulus that you use for your calculations. You can either use this table, which is a smart thing to do, or you can use this formula. This formula gives us a more accurate one, but it's literally like, just use these ones. When we're designing, we always use these ones. Okay? So, have you guys opened the AS3600 at all yet? No? Okay, good. That is very much expected. I don't think I've opened it that much. Okay. But, what can I explain really? There's a lot of math going into this, which I'm not going to bore you guys with. The main thing that I want to talk to you guys about is the difference between using the mean value and the characteristic strength. So the characteristic strength, I'll draw a diagram for it. You guys have seen the normal distribution, right?
Yeah.
Just turn my camera on, please. Yeah, this is a bit of 2002.
I need
So-
to look back into it.
Okay, good. So, that's your normal distribution. In the middle, you've got your mean, FCM. And then over here, F dash C. Yeah? You know you see it.
You blind?
Okay. Right, so, as you guys know, when we're designing, we design for the worst case scenario. Right? That's why we take the last 5%, which dictate, or this is actually how they calculate F-C, not through like apparatus and so forth. I think this is how they figure it out. So they take the F-C M, so they do a bunch of tests to like figure out Z values, Z whatever, right? And then they calculate this using like statistically. So,
But
huh?
what is F dash?
It is your characteristic compressive strength. Like, at 28 days. So when your concrete, after it's poured, 28 days later, they
So it's the compressive strength of the concrete. But like you're saying like like how it's made, like the concrete compressive strength could be different, but it's a general like normal distribution. Okay. We take the like the worst case, 40 made like the compressive strength. The like the concrete what's it? Each concrete when it's made, it's like different compressive strength. It's not consistent, right?
Mm-hmm.
Yeah. So and we're taking the bottom 5%.
No, well, what I'm saying is that for that pour, you'll get like a compressive strength.
Yeah.
Yeah, I think you're right. But like the main thing is that is it 5%? Yeah, so this 5% represents defective. And so there might be defectives all around, right? But this is like where it's most common, obviously, like the most effective. And then you might be wondering why don't we just take the worst case scenario? It's too conservative, right? Meaning that you're just over exaggerating for that, like you're just doing it too much. You're doing too much. Right? Over here is like it's like a safe balance. It's like a balance. Yeah, I think that's like a very bullshit explanation, but
FCM is a mean
FCM is
compressive
mean.
strength. Okay.
There's really no explanation to it. Wilson, would you be able to explain why F-C is the last 5%? My structural engineer.
Huh?
You know that F-C is the last 5% of the thing? Yeah, I'll tell you, yeah. Why are you shaking your head? It don't even matter. I don't even know.
What does F-C stand for?
Are you serious?
Forgot.
The compressive strength at 28 days.
Oh, at 28 days is the strongest, isn't it?
Yes.
But get this guy out of the class.
No, that's right. Just trust me, we've done this so many times and we actually figured it out.
It's the strongest. So why you use the strongest?
No, it's fine. It's theory. I'm trying to explain it, but like I can't even explain it because I actually don't know. Like
What's the part that you can't explain about?
it's like why does like unwashed.
Why would you use the bottom 5%?
Yeah, why is the bottom 5%? Like the best, what I explain, it's like the worst case scenario, it's the worst 5%.
It's like the safety factor thing, right? Like it's
It's to do with the safety factor.
Well, of course, we're not gonna take the best case because then that's not,
people can die.
people could die because it's all.
No, there's like an actual reason between the difference between characteristic and mean. Do you remember? Didn't Timber?
But is this in our course?
No.
Oh, you're
So-
saying like why don't we take the bottom 10%? Like why is it 5% specifically?
No, it's fine. No, like this is from your lecture slides, but they're not gonna test it like as a theory question. Unwashed. Anyways. Properties of steel. So steel, obviously it's really strong. Its yield strength is very very high, between 250 to 500 MPa. You'll see later on there are different classes of bars, right? I'll cover that in a bit. And it's also very stiff, meaning its E value, elastic modulus, is 200 GPa, which is MPa. So for concrete, usually you can see the EC values here. So you can see how much more stiff it is compared to concrete. So it provides usually a bit of stiffness. Connections, don't worry about that. Economic, don't worry about that. Disadvantages, durability is a very big factor. So staining, rusting, chemical attacks, all those kind of stuff is a bit of a problem. But what I wanted to kind of explain is the stress strain graph. This is something straight out of the material. So this is like a material graph, right? You've got a couple different points. You've got your yield stress. You've also got your ultimate stress. So the distribution up until yield stress is linear. Okay, so we're gonna, when it comes to something we covered as well later on. You guys know rise of a 1. So the reason we can use this equation is because it's linear. If it wasn't linear, then you can't really use it. Now the other thing is ultimate strength. This is where like so yielding, there's like all those things that happen like necking, plastic deformations, all that kind of stuff. Not covered in the course at all. It doesn't really matter. I'm just kind of trying to go through a bit of background knowledge. Over here is where it like becomes fucked. Alright, like that's when your bar like actually breaks. Right? Well, no, sorry, that's over here. But like over here is like, it's like the yield stress is decreasing because you just can't take enough, and then at one point it just fucking disintegrates, or it just explodes. What matters is this value. Usually it's zero. I say it's usually 0.0025 because, again, E is this over this, yes, strain. We said that E is usually 200 times 10 to the power 3. Your yield stress is usually 500 MPa. So when you rearrange, you get this for your strain, yield strain, right? This becomes very, very important in the next part of the lab. So I'm going to cover a bit of design. And you can see in design, we use over here to check out ductility, to figure out our forces as well. There's like a bit to it. Okay. This I'm gonna quickly cover. So I'm just taking pictures from your lecture slides to kind of just briefly explain each of it. Right? So there's two kind of bars. We've got plain bars and deformed bars, right? Plain bars is usually just a cylinder, right? Deformed bars is with the ribs. So these are what we call ribs, like there's tiny deformations sticking out the bar. That's what we call deformed bars, right? Does anyone know why we would prefer deformed bars over plain bars? Perfect. Yeah, exactly. So
I don't know why there's so many different types of things.
yeah, I don't know. Usually in Australia, the ones that we look like looks like this. Alright, so 500 bars doesn't get industry standard. But the reason why we have those ribs is, imagine we have concrete. So imagine this is my bar. Okay, so this is bar. Anyway, as you pull out, pause, what happens is so imagine this is your plane bar. Pulling this out. Sure, there's a bit of friction here, right? But you see the concrete in this area here. It kind of, as Ray said, provides like a better bonding. Yeah. So
It's just more surface area.
pieces in this. I should know. It's called mechanical interlock. Do you fucking work? I guess you just gotta imagine that like over here we like slide right out. But over here, like because of the extra concrete there, kind of doesn't come out as easily. Does that make sense? I'm thinking of a better way to explain it. Fuck, I should write for this. So here it is. So the ribs. Fucking hell. Oh, okay. The actual reason is a bit techy, but what it does is, there's also going to be some friction here, but there's like stresses that get put on these ribs, right, which makes it harder to pull out. Essentially. That's all I'm going to say, because it's not too important for them. Hopefully I didn't confuse you guys too much. I'll just be yapping right now, I'll be honest. Okay, the main thing I want to cover really quick is that there are two different kinds of bar classes. We've got the R bars and we've got the M bars. So we've got R. So when it comes to reinforcement, we use this. But when it comes to something you guys will learn about, fitments, shear, reinforcements, we'll learn like later on. We use R bars usually. The only difference is this one is 250 MPa. The yield stress. So this one reaches yield a bit quicker than this one.
But it's like a cheaper, like why would you stop that?
There's a lot of geometrical properties, I'm pretty sure. Oh, sorry, it's not R bars, so it's L bars. L and M, sorry, not R. There are economic properties to it as well, economic differences.
Wait, like it's like
No, I think it is
bars
like-
like material difference, or is it like the form, shape difference?
Oh,
Or is it
material
different? Oh, material.
material properties are different.
Okay.
Right.
What is the E-bar?
Don't worry about it. It's earthquake bars. So this is something that you get in your exam, something very similar. You'll get these two. So these are different diameters. So N, 10. So N is like your normal bars, and then the 10 is just the diameter of the bar. Right? So these are nominal areas. So you can figure out your area manually using pi r4 d squared. So pi r4 times, if I did 12 squared, that'd be 201 point something, 201.34, whatever. But we just take it as 200. Yeah, nothing really much else to say. Not important. Not important for this course. So I'm not gonna cover this. Hey, a bit of a demonstration now. I'm gonna get, how many, 1, 2, 3, 4 people. Let me draw up 4 diagrams. Listen, can you drop a graph for me?
I don't have work to do. Like,
Drop a beat for me.
Yeah, a bit.
Yeah, with supports and everything. You kind of
Oh, sorry. Or something different.
You can see she's good.
bro, pop.
Oh, you covered everything.
Because I watched Henry.
it won't change it.
Did you go to Henry? What to do? What? Oh, but I haven't.
You covered everything. Hot from a candle.
Oh, I can't do it.
So why'd you go?
Why didn't you go last week?
What if just a candle?
Okay.
That's what Henry does.
He draws like a
Exactly.
spider.
Oh, my.
Okay.
This is why
So where do I know how to place a rear is the main question. If you guys were at my concrete crash course, you should know.
Put it in place of tension.
Tension, exactly. Good. Oh, exact answer. Yeah. So the main thing is words and tension. Right? For those who haven't done 2, 3, 3, let me.
Oh my god, I'm doing the courses with you.
What are you doing next time?
Yes.
So what is the bending on the diagram? Normally. Like that? Yes. So the bending moment diagram looks like this. Right? With the positive up front. But
Oh, is that the convention?
this convention is incorrect.
Yeah, I do it the other way.
Normally, well, you guys should,
Show the way there.
you guys will learn that in 2, 3, 3, the proper convention is you draw the positive at the bottom. Right? The positive stands for tension. Why do we draw like this? Does anyone know?
Because it shows the strength of the
He's on fire.
Dude,
No,
you're
I also got, I asked Henry this in the crash course and like he told me.
Oh, yeah. Yeah, so pretty much what it does, it kind of represents how it's going to actually deflect as well. Alright, so you got to think about how it deflects. Fuck, the camera's not on. Sorry.
Turn it on then.
So that's pretty much how it's going to deflect. Alright, so you can see that it looks pretty much the same. Same thing with a cantilever. I don't want to do that. But the main thing is, whenever it's in tension, right, decide its intention is where you place your reinforcement. So for example, in this first example, since this bottom side is in tension, I'm going to have my rear back. Yeah? You okay? Yeah, But if you were to like kind of look into a microscopic level, like imagine these are fibers, right? Right? That's one.
That's all good with this.
Actually, oh, okay, cool. Pretty much what happens is these fibers at the top, they're gonna like kind of squish into each other. Oh, okay. So this is gonna be this, which means it's in compression. Right, the top fibers are in compression. The bottom fibers here. Imagine these are my fibers. Right, what happens is that these fibers are gonna like kind of pull apart, right? Which causes cracking. Like I said earlier, tensile stresses causes cracking. And then because your
Concrete
Right, he just
Yo,
took
get
it.
him up
What?
there.
Right, get
Yeah.
up here right now. Now, yeah, because your concrete's in weakened tension. What happens is you're gonna place those bars there. Okay, I'm going to a bit of detail for no reason, but fucking Jen, since you're laughing, can you come up and show where the bars should go here? What does that mean? Wrong, right? Where would the bars go here? So you just remember from the crash.
Because I watched Henry's thing.
Good job.
Wow.
Hey, yes. This is correct.
What was that?
So Michelle, I'm gonna give you a special one. Go
I
on.
promise I don't know. I have not
Madam?
watched a single.
Bottom top.
fucking come up and do it.
Are you doing the cantilever?
Who are you talking to?
I'll tell you exactly.
I'm
what
talking
to
to my
do.
boy.
Goes, you see that? Ooh.
Yeah, that's good. That's correct. Because like the way it's gonna deflect, it's gonna deflect like this. So you can see that this part, this top part is intention. This bottom one is also intention. Lay down. Let me make one for some action.
No, don't. I haven't watched a single comedy lecture for Han stuff. Stop.
Like listen
Oh shit, it's a long ass bar, bro.
Stop it.
You know, like this?
I got it into the wall and everything.
Wait, but it needs to be
That
in the
is
wall,
nice.
yeah, for the cantilever. Because then
Good
that's
point, but you doesn't. For our sake, you're going
Okay.
to take you.
Okay.
Oh.
Like, yeah, no. That's a very good point.
Future little North Rock for
Like,
Oh.
if you want to get even more technical, like you do like
Yeah,
That little hook.
Yeah, the hook.
Oh. Shut
Wait. Okay, no, but real question though, like,
Yeah, go
the hook, yeah, like, for example, this one's supposed to have a hook. But then
Yeah.
why not the middle one then?
So, okay, this is covered in detailing, right? The reason we have the hook is there's a requirement in the code, if you remember.
It like halves the like bonding.
Yeah.
The relevant length,
Oh, yeah.
right? So pretty much it's the amount of bar that's required to, extra bar that's required to like letting the, I'll fucking know. But it's to let the bar reach yield stress, right? So it needs that extra thing to bond over to allow it to reach yield stress, right? However, the thing is, it might need to go outside the concrete itself. But obviously that's not possible. So what you do instead is you hook at the end, and it provides 50% development.
But for the development, like, I think the best way to describe it, Henry used like glue. Like, if you have like little glue, it's not gonna be bonded. But like, if you have like a lot of glue like this, it's harder to separate. So that's why like they put like extra bar just to hold it.
Yes. That is a good way to explain.
But then like,
That's a very good way to explain. Yeah.
but then how does the bar like?
Alba.
Is it just for like so?
No, so that analogy is pretty much just saying that you need more glue.
Yeah.
You need more.
Oh, so just putting it up like that is just making it longer, but like not by expanding it.
Yes. It has the same effect.
Okay.
And then in the middle, the reason we don't hook in the middle is because all you can do is use that 10 hours of that.
Oh yeah.
Okay, one more.
Han stuff. Move next question. Next question.
Wait, do the standing up one. Do the standing up one. So it's
The
stand,
one
like a
that's
stand.
like this.
Yeah, stand up.
Don't do that. That's
Oh,
terrible.
your yap is going too long. Sit down and keep.
Nah, I've got an extra 5 hours.
Sit your ass down. We leave it. Your camera not even on, by the way. Oh, what's this little lecture?
Why have they made a whole K-drama?
Okay. Let's get you go. Get her out of here. Get your
Talking about.
Oi!
Group leader.
Bring some people together.
My legs are
Yeah, I'm shouting like.
No, anything. Ask me a question.
Biceps are
Yeah,
real.
because it's you're bullying people.
Yeah.
You used to do that to me
Well,
when
your
I was in
lectures,
college.
your
Yeah, and now look at you pass all your posts.
Shut the fuck up. That's because of tea.
Fucking pause the recording.
Oh my. Actually, DT.
Bit of a trick question.
Make sure that was tough.
Good job, dude. That's tough. That's freaking tough, yeah. Okay. Next part to really cover, I'm literally just gonna look at the slides here and kind of explain it because I don't have notes on it. But the design process. So there's a couple of things: durability and fire protection. So you gotta account for durability depending on where you are in Australia, right? So there are different zones. You've got a tropical zone, temperate zone, arid zone, blah blah blah.
I put on my shoes and he took them off.
Yeah.
And then pretty much depending on your exposure classification, there's like a minimum.
Did you start the recording? Oh.
Yes, I did. And then a minimum cover that you need as well. Here it is. So, what cover actually is? It's funny. So, if you take a look at your concrete, so this is like a cross section of your beam. You've got your bars like this, but your bars have to be a certain distance away from the outside, right? From the outside here and here. That's what we call cover. Right? So usually what will happen is that you also have bars running like this. That's what we call fitments, stirrups, and then the distance between the middle of this bar. No, is that cover or clear cover? Clear cover. Clear cover is distance between this to here. This is the gap that you need. Right?
Is this from the center of it or the?
So there's two kinds. There's clear cover and just. Is it normal cover?
No.
What's it called?
I don't think you use cover. No, like that cover.
Yeah, I don't think there's no
you
normal
don't,
cover.
you don't go into the diameter.
Yeah.
You just go to the edge.
Oh, I'm thinking about neutral axis or diesel.
Oh.
Oh, type shit. Okay, so there's something called clear cover, right? Which is you take a look at the outside of the bar. So imagine that's the other bar. Okay, let me actually draw this properly. Cool. So okay, that's my stirrups. The distance between the edge of that to the edge of the concrete block is what we call clear cover. Okay? So that's to prevent rusting, fucking whatever, chemical attacks, all that kind of stuff. Right? That's why we have it.
Oh, so there's only one cover there, that's big.
Clear cover, yeah.
What's it made of?
Huh?
What's it made of?
Huh?
What's it made out of?
Oh,
No. Clear cover is just this distance.
It's like the distance from the
It's not like a
with the
material.
steel bar.
Oh, they have a diagram right there. Oh, sorry. They have a diagram right there, yeah.
Wait. This is also steel, yeah.
Yes.
Okay. So then, what about this? What's this?
That's part of the steel.
Oh,
So
that's
do you
also-
remember the hook and cogging and stuff that I was talking about?
the hooks. Oh, is this the hooks?
No.
Oh.
It's hooks for. There's two kinds of reinforcement. You've got your primary reinforcement to prevent bending, tension failure, all that kind of stuff. But if you want to prevent shear failure as well, you need a different kind of reinforcement. And
Wait, how big is that?
no, not yet. It's covered in shear. This is what it looks like. There's these stuff here. If you can kind of imagine it, like not even imagine, like look at the photo. That's the shear area. This is their primary area. Make sense?
Wait.
Fuck
Hold
no.
on. So okay, I get this is like this is also steel, but I'm saying this though, like.
Yeah. So if you can see, oh, you can't really see.
Oh wait, I kind of see. Like, they kind of wrap around the steel bars.
Yeah, you see that?
Oh yeah.
Yeah, it's like wrapped around.
But
See?
that's for shear stuff.
Yeah, it's for shear area. So going back to this, yeah. So the cover is that. Next thing. Corrosion protection. Wait, have you guys learned about limit state? Design load combos, Jen should know it. Yeah. Anyone know
So
load
it's like
combos?
the live load. Yeah, it's we cover it.
Yes, that concept. I think I explained it pretty well in the crash course, so you guys can take this is getting too techy with it, I'll be honest. So I was trying to explain it in a techy way earlier, like using the no one just let him try. But what I will do is I'll go through like a quick example of
What about for concrete, there's also like assignments.
sorry?
There's also like you kind of do the assignments for each of the weeks.
Yeah.
Is it done by you as well? It's like did you write
There's a combination. Me, I did some, Henny did some.
Because like we kind of it's copy pasted. The question.
They might have mistakes. I'm gonna go over them like as you guys do your assignments. I'm gonna go over them and check them. Like the not your guys' work, the fucking thing. But yeah, a few examples. Imagine you guys have a beam. Right, quick example. Right, this loading, you've got two parts to it. You've got live load, you've got dead load. 5 kilonewton per meter, 3 kilonewtons per meter. Right? How do you figure out the load actually acting? The factored load, right? Yeah? This is straight from AS 1170. Right? So it's standards, Australian standards, right? So you gotta find the maximum out of those two values. So you sub in G, which is at dead. Then you sub in Q as well. Figure out which one's the bigger value, and you take the maximum. And what that means is that later on, when you redraw your force body diagram, instead of drawing it as two different loads, you can just draw it as one. So W star is equal to whatever value that is. Yeah? And then you just do your normal static analysis from there.
What if there's like a distributed load like this and there's also like a point load?
Oh, very good point. Very good point. If there's also a point load, okay, the point load, they'll specify whether it's a dead load, but usually point loads are going to be live loads. They're usually live loads, yeah? So let's say this is Q. Because you gotta use 1.5 Q. What's up, Henry? You gotta use 1.5 Q. Why 1.5 Q? Because the load combo is either maximum of 1.35 G or 1.2 G plus 1.5 Q. Yeah, but in this case, it's only a live load. There's no G to it, so G just becomes 0.
So can you just treat like it's distributed?
No. The factor, it will stay at point load. The only thing that you're doing is you're factoring it, which means you're making it larger. So it will stay like this. So this will become W star. This will become Q star.
W star was a factored load.
It is a factored load.
So like the same beam can have two different loads. I mean, two different packet loads.
No, they're not different loads. Like, oh sorry. When I mean by different loads, I mean like they're not different to what's going on. Fuck.
Right, you can put up the assignment. This assignment.
Does Simon have it?
He just wants you to do this.
So like.
Okay, I'll do the assignment, bro. It's alright. I'll do it. Like this? Bless you.
What's it called? It specifies that this key.
Okay, you can see here that, bless you, we've got G, which is acting on the beam, a Q that's also acting at the beam at the same time, bless you, fucking hell. And you've also got the live load, the point loads, right?
Yeah.
Point live loads,
Which
so
is B and D.
B and D, right? So in this example, yes, you. Hey,
I broke one of those letters. So like,
alright, this is the example, right? Yeah? So after I factor everything, did you have avocado?
yeah, that makes me sneeze.
I don't know.
Idiot.
It could,
I'll
right?
vomit from it.
What happens if you don't vomit?
I swear to God.
Shit, right?
Yeah, on camera and everything. Nice.
And then this thing becomes. Take a look. Take a look. Ray, that's what happens after you factor it. Alright? So you're applying the load factors to it. Yeah?
Okay, so you just times with the, like this, it's like an individual load, so like with live load, it's 1.5. Okay.
Yes. Make sense? Well, like it's easier with some examples later on.
Yeah, that's how I'm doing that.
So great.
Okay, bro, I'll go to the assignment with you. It's alright. See, there's also this part here. So these are some good examples. So you have your dead load, live load, DLLL. Oh, see, these are comparing the two different cases. 1.35G, 1.2G plus 1.5Q. Yeah? And which one would you take out of those two? 30, yeah, because it's larger. Alright, cool. Okay. I think I might leave it there. Because I think next week I'll just cover all of Flexure. Next week. Fucking Flex week. Hey, do you want to take over Flexure? Alright, we'll leave it here.